Hi, my name is Divit, and this project is a comparative study of three reinforcement learning from human feedback algorithms PPO, DPO, and GRPO applied to Google's Gemma 3.1 billion language model using the Stanford Human Preference dataset. Large language models trained on raw internet text are fluent, but they are not naturally helpful, honest, or harmless. Reinforcement learning with human feedbacks fixes this by training the model using human preference signals rather than just predicting the next word. This pipeline contains three stages. First, supervised fine-tuning. We show the model human written examples for good responses so that it learns to follow instructions. Second, reward modeling. We train a classifier that can score how good a response is by learning from human preference pairs. Third, reinforcement learning optimization. We use the reward signal to push the model forward, generating a better response. For this project, I used Gemma 3.1 billion parameter based model and then Stanford Human Preferences dataset, which is taken from Reddit, and Open Assistant debug reward model for scoring. And I've used Google Colab for running the whole experiment. This diagram shows the full pipeline across 5 different Colab notebooks. First, supervised fine-tuning on 800 examples for 2 epochs. Notebook 2 runs DPO, Notebook 3 attempts PPO, and Notebook 4 runs GRPO, and Notebook 5 is evaluation notebook, which loads all the 3 trained models and scores the responses using the reward model to produce win rates and reward comparisons. In Notebook 1, the key design choice is LoRa with rank 32 applied to all linear layers for, of course, attention and MLP. This transition only takes place for 1% of the whole dataset, keeping the base model frozen. The function format for SFT function converts each SHP row into Gemma's chat template, which picks the preferred response using the score ratio field. The training ran for 500 steps and loss dropped from 36% from 3.13 down to 2.12. In Notebook 2, the same SHP data is reformatted into triplets, prompts, chosen and rejected format. The DPO uses these triplets directly without even loading them into a reward model. The DPO encoding only needs bit beta, which controls how far the policy can drift from the SFT reference. The standout result is loss dropping from 0.7 to 0.06 at 7,000 epoch. The model strongly learned to separate good responses from bad ones. The Notebook 3 is where things went wrong. The PPO loop generated responses, scores them with dbeta, and then runs a gradient update. In the previous run at step 40, the KL divergence hit negative 14 in run 1, and then I had to rerun the whole thing again, and then it went positive 45.56 in run 2. Both are catastrophic. The value head of PPO requires to estimate advantage was incomplete with Gemma 3's architecture is what I have concluded. Notebook 4 fixes the PPO problem. The key difference is num generations for GRPO samples 4 responses per prompt and uses their average reward as baseline instead of learning value network. No value head, no critic, no instability. The reward function scores all 4 responses with dbeta, and GRPO computes relative advantage within the group with 200 steps within 28 minutes, completely stable. In Notebook 5 loads all the three models, asks them the same 10 questions and scores every answer with DBERTA's reward model. Then it computes them head to head. SFT scored negative 1.8. It can follow instructions but not aligned with human preferences. DPO scored 0.9 and won 75% of the matchups. GRPO scored positive 1.05 and 160%. Both are significantly better baselines. The failure of PPO's algorithm is one of the most interesting findings in this project. The PPO algorithm is used in Instruct GPT and ChatGPT. It is theoretically the most powerful out of three, but it requires four components in GPU memory simultaneously. The policy model being trained, the frozen reference model for the KL penalty, and the reward model and the value head acting as a critic. I ran it twice, but in run 1 with the default settings, the KL divergence crashed to negative 14.3 at step 14, and a negative KL means the policy was assigning lower probability to its own outputs than the reference model. This is a classic reward hacking. The model found the adversarial responses that scored well on DBERTA without being genuinely useful. I tried to fix in the run 2 by reducing the KL coefficient from 0.2 to 0.05, and the opposite happened. The KL exploded to positive 45.6, far beyond the target of 6. The root cause is that the Gamma 3 model attention architecture is incompatible with TRL's value head, producing unstable advantage estimates that cascade the KL failure. The training result summary for all stages. The SFT completed in 26 minutes with 500 steps with 36% loss reduction. The DPO was the longest run with 44.6 minutes, 714 steps. Loss oscillated from 0.5 in one epoch and dropped sharply to 0.06 in epoch 2. The proximal policy optimization training failed nearly at step 14 in both runs. The GRPO completed in 28.8 minutes for 200 steps. The loss oscillated around 0, which is expected, and remained stable throughout the training. Quick overview result across models. The top left shows our average reward. SFT performs poorly while DPO and GRPO significantly improve their alignment, with GRPO slightly higher. The top right win rates. SFT wins only 10%, while DRPO leads 75% and GRPO follows at 60%, confirming strong improvement. Bottom left per prompt scores. SFT is mostly negative while DPO and GRPO are consistently positive. GRPO is more stable and DPO has higher peaks. The bottom right explains PPO failure. The KL divergence explodes and reward drops, showing training instability. For evaluation, I tested SFT, DPO, and GRPO on 10 diverse prompts and scored them using a DBERTA's reward model with head-to-head comparisons. Looking at an average reward, SFT at negative 1.8, while DPO and GRPO perform much better, with the GRPO highest at 1.054. However, the win rates, DRPO leads with 75% wins compared to 60% for GRPO, showing it's more consistent. GRPO achieves higher peaks but with more variance. Finally, PPO fails completely. So use of DPO for reliability and simplicity, and GRPO when you need online learning despite some variability. I'll leave you with two questions to think about. As language models grow larger and more capable, which alignment algorithm would you trust more and why? And if PPO is theoretically the most powerful reinforcement learning with human feedback algorithm, why did simpler method outperform it here? And why does What does it tell us about the gap between theory and practical in AI alignment?